Okay, we'll get started. So welcome back. I'm actually, so many people have been talking about being interested in manipulation and legs that I'm going to do one extra lecture than I've done in the past about planning through contact and control through contact, because we haven't gotten to the best stuff yet. So I'll try to get to the best stuff today. So the last few lectures, we've been introducing and using pretty heavily this hybrid systems view of the world, right? So and the picture I tried to give you last time that I think is the right way to think about the hybrid systems models is that you have x dot is f of 1x here. Maybe it's got a control. Maybe it doesn't. X dot is f2x here. We have an event that happens when you smack into when your foot hits the ground, or whatever, your hand touches the object, that's defined by some guard, the level set of some guard, where phi of x is greater than 0 over here. And then you have this reset map, which is your impact dynamics, right? And in that inside that framework, I mean, we've done this even before I started drawing this picture. We had done this with the rimless wheel, right? Where the idea was that during the stance phase, we were just thinking of it as the dynamics of the pendulum. Explicitly, we modeled the event of the foot hitting the ground as a discontinuous event, which was a guard in our phase portrait, and then there was an explicit jump, which looked like cosine of 2 alpha. You lost velocity proportional to cosine 2 alpha in the jump. When we got to this next, the other thing that the jump did was it actually reset our coordinate system so that the whatever foot just hit the ground became the pin joint for the pendulum, and you started again. Right, so we made heavy use of this sort of modeling approach in the rimless wheel. I didn't go into as many details on the board, but the same thing true in the compass gate. Certainly the same thing was true in the slip model. These all lived and breathed the hybrid systems modeling phenomenon. In the slip model, maybe in particular, right, the flight phase, when you're off the ground, we even had the coordinates, let me even just write the positions. The coordinates were given by, let's say, the xy position of the mass, because the leg didn't actually matter. And in the stance phase, we suddenly had a pin joint at the base, and we were able to think about the dynamics in terms of the polar coordinates of the leg, r and theta, and we could, from that, knowing that this was pinned at a particular place, the xy condition comes just out of polar coordinates from that, and we were able to write, and we actually use a different state space representation in different modes of the system, right? And then the reset map's job was to relate those two coordinate systems, right? To say, to do the kinematic transformation from x and y into r theta so that the conditions line up. You know, that's hugely powerful for a number of reasons, right? So, first of all, in this paradigm, you can do very accurate simulation, right? Because if you specifically tell your numerical integration tools about the existence of this guard as a witness function, is the language in numerical integration, it will, as it integrates, check the positivity of this function, check to see if it ever crosses that function, and then do explicit event detection to find the moment of zero crossing. Right? So there's, zero crossing detection is the more sophisticated integrators have them. And they'll tell you, okay, I've zeroed in to what arbitrary accuracy this event, and then you can apply your reset map with some confidence and continue on your way. For trajectory optimization, this was also really nice. Right, we could basically take the tools we already had, and at least for the case where if we know the mode sequence, right, then for instance in the slip model we could populate some constraints in x and y, the first n constraints or k constraints in x and y, the k minus 1 to whatever constraints in r theta, right, and then so on. I could fill that out using f1 when appropriate, f2 when appropriate, and then my guards and resets just add additional constraints, right? I think that's yet another reason why I prefer the the transcription methods where you have explicit state representations. It's really easy to add on additional constraints as opposed to the shooting methods where those are less natural to put on. Okay. So really, there's a pretty reasonable way to do trajectory optimization, and the walking community has been using those tools to develop gates and the like for years with a lot of success. For stabilization, we talked about LQR along a trajectory. And again, the tools basically work, right? And the idea, just to summarize, was that you would use the continuous, it's not an approximation, the right thing to do is to use the continuous Riccati equation in each mode, and you end up using one step of the discrete Riccati equation backwards in time. Across the resets, which looks like one step from your discrete time LQR that gives, if given the reset map and the linearization of the reset map, it tells you how your cost to go matrix projects into the original state space, the state space on the other side, and then you keep going. And we've always referred to, I got this from Ian Manchester when he was here, I've always called this the jump Riccati equation. And nobody said that's offensive or wrong, but I have had a few people say, like, oh, I never heard it called that before. So, not sure if that's mainstream notation, but I love it. Jump Riccati equation. That's just putting those two together is that you continuous and then jump and then keep going. Okay, and we even talked about doing sums of squares along trajectories, right? Or Lyapunov analysis along trajectories. Just quickly at the end. And it was, again, the game was to stitch together the tool we already had for continuous time with a discrete update, and then the tool we already had for continuous time. Right? So in this world, it's really, life is good. We pretty much use our continuous tools, and if we just stitch that together with our one of our discrete time tools, things work out. So what's the pain point? Why are we not done? Okay, the pain point in that framework, and we saw a glimpse of it, and whether you caught it or not, but you saw a glimpse of it coming when we were getting into the details of even the Lyapunov sums of squares. We started talking about the transverse coordinates, and there was a subtlety where the transverse coordinates had to line up with the guard. Okay, and I'll say that again in a second, but that was that was the first glimpse of the problem with these tools, okay? And the problem with these tools is it doesn't talk about how do you do stabilization across different contact configurations, okay? So in this picture, you know, when I'm here and I've got my nominal trajectory here, it's telling me how to close that gap, right? The problem is, what if I'm supposed to be here, my nominal trajectory is here, but I'm still over here? What's the distance, you know, in fact, like, look at that, right? So if I'm going to try to stabilize x bar is, you know, x of t minus x0 of t. Okay, what if those don't have the same units? Or they don't have the same dimension even, right? The problem, the big problem in my mind with hybrid systems modeling is that the framework as a whole is too general, in the sense that in the hybrid systems language, you could be going through a wormhole effectively, right? There are two disconnected dynamical systems. There is some wormhole that takes you between them, and there's no general way to talk about distance across a wormhole. I guess, the problem is I don't know how to stabilize across wormholes, right? That's still an open problem, and that's sort of fundamental, and it's pervasive. If you look at the limitations of our best controllers in walking robots, in manipulation, and other things, once you get out of your expected context, if you have a plan and things are going according to plan, things work really well. When you have an unexpected contact that takes you out of your expected contact situation, things get really ugly really fast. And that's where the blooper videos from the DARPA challenge came from. For us, it was our butt hitting the seat, and we were in a mode that we didn't realize, and we didn't know how to go back from that mode to the one we had planned for. Okay? So the pain point is stabilization across modes. Right? There's really no guarantee. The general, you know, F1 of x and F2 of x could be arbitrarily different. Okay, so let me say the Lyapunov thing again. So the transverse coordinates, and you asked a good question about, is the transverse coordinates about periodicity, or is it about stabilizing a trajectory? And there was a subtle answer that I wasn't giving you well, partly because I needed this to say it. But okay, so even if it's not a periodic solution, the transverse coordinates are trying to make this problem a little bit better by saying, if I'm going to try to do stabilization, I can come up with a transverse, I can come up with at least a mapping that says, even if my nominal trajectory was over here and my point was here, that it's okay to project and act like the controller here. Okay? Similarly, if I wanted to make a statement about, for all x in some tube, the Lyapunov type statements, I cannot make a statement that has to cross this boundary. But I need to make a statement about all of the states that lead up to this boundary, mapping to all states that exit this boundary. So it was very important that our transverse coordinates lined up with that reset map, and then the funnel on the other side lines up with that reset map. Okay? So that was the reason that transverse coordinates ends up being somehow coupled with collision and impact is partly because of orbital stability, but also because of this. It helps with this problem of trying to stabilize at least up to the contact. Still not across, but at least it gives you a way to project if your time is getting ahead back. Right? The transverse idea is roughly how do you make LQR safe under the projection of going to the closest point. Okay, but the goal for today is to think about, how do you stabilize a cross? And if it's a black hole, then you've got a wormhole, then you've got no opportunity. But rigid body mechanics is not actually just this arbitrary jump. So let's think a little bit more about the formulation and see if we can write down sensible ways to think about distances across contact modes and stuff. Okay? Oh, by the way, I made a mistake at the end of the last lecture, and a couple of you caught me on it, right? So when I wrote the conditions down in the transverse coordinates, I said that just dv partial x perp dot had to be less than or equal to 0. And a couple of you came up and asked, how could that be sufficient? And it's not sufficient. That was a mistake. I apologize. So I should have written dv dt. The whole thing has to be true, because and which is, as we talked about right after class, of course, that has to be true. So I apologize for that mistake. Okay. So how do we do better? Let's think about other ways to write down these sort of contact mechanics. So something subtle that was happening here, in addition to the fact that we could write down accurate simulation, trajectory optimization, and the like, there was something else that was good that was happening here, which is that I'm writing the system down in a very compact way, in a way that was called minimal coordinates. Okay, we call this minimal coordinates. And we're going to have to give that up in order to get across contact sequences, but that's okay. We can give that up a little bit. So, the first idea is to go to a maximal coordinates, and it's typically in at least ligand robots, you think of that as the floating base coordinates. Okay. Okay, so the new way to model the rimless wheel is I've got a rimless wheel falling through space, okay? It may or may not be on the ground. At every potential contact point, there is some force that could be applied. My rigid body model has lots of possible forces. These are just arbitrary directions, sorry, but not meant to apply anything or even directional. I mean, whatever, okay. But the point is, at every possible contact point, you have a force. And if you do that, these forces come into the equation in a very standard way, okay? So the manipulator equations turn into something like this. Okay, so most of this is familiar. Sorry. This is now my contact force. If I have many of them, then I have a sum of these forces. This is a 3×1, Cartesian contact force. Sorry? Tau G. Oh, thank you. I got too carried away with my Q's. Thank you. There was a lot of that way, right? This thing is the contact Jacobian, which I'll say more about in a second. And really what's important is that these contact forces enter the manipulator equations in a very structured way. The manipulator equations are affine in the contact forces. We're going to exploit that in a couple different ways. Okay, and we already said that there's a totally reasonable way to work with these, right? So, right, I talked about, if I have my foot penetrating the ground a little bit, but I can draw a spring that's sort of providing some resistance coming back up. So you could imagine writing the dynamics here where the Jacobian roughly tells me where my foot is in space. That's the derivative of that. Okay? And then the forces I try to apply at those are just a function of the amount of penetration that I'm experiencing, right? And similarly, you could put a resisting frictional force that has something to do with, for instance, the velocity of the contact location. Okay, but given the floating base coordinates of the rimless wheel, I could figure out where all the feet are, set the forces to 0 if they're up in the air, set the forces to something that's pushing me back out of penetration if I am inside the ground, and then set some horizontal, some forces along the length of the ramp to represent friction. And you can come up with your own friction law for that. Okay, that's a perfectly reasonable thing to do. You have to potentially reason about lots of forces. Of course, if you're simulating, you would only ever think about the forces that actually went inside here. But if you're going to write optimization problems, you might have to think about all of them at once. Okay, so what's the state space of this now? The state space of this is probably x, y, theta. So I went from a 2-dimensional state space, which was my theta and theta dot, up to now a 6-dimensional state space that I'm thinking about. And this is also called maximal coordinates. Okay. Okay, so this is a good, this is something that people really do using these spring models. But most of the people that do that do it for simulation, not so much for optimization and control design. Do you remember why? I used it quickly as a straw man before when I introduced the hybrid models. There's some obvious ones and there's some subtle ones. Why would that not be a great thing for optimization? Why is it trickier for optimization? So you might be making more variables, which that's going to be true as we write this out. But it's also, if you think about the way that people simulate it, the problem that I called out before was that the spring models typically lead to stiff differential equations. So unless you're a rimless wheel on the trampoline, right? Where, but somehow, if your dynamics change very discontinuously as you go from, before contact into during contact, then almost by definition you've written down a stiff differential equation. Okay, so why is that painful for our optimization tools? I mean, for simulation, there's good tools for solving stiff differential equations. You could have a variable step integration that's even monitoring your accuracy. When it comes into contact, it will automatically schedule smaller time steps to be taken as the simulator proceeds. And then as it comes out of contact, it could then increase the time step of the simulation and be efficient again. Like, it's almost comical if you're not careful when you start, you run a simulation and you turn on the stiff solver. The accuracy is great if you don't have to think about it, but when if you've watched the playback as it's simulating, it's like whoosh, whoosh, it defies, it breaks your. We have to actually engineer the tools to make sure that it played back in real time, just because the things looked aphysical when they would hit molasses every time your foot hit the ground, right? And but the solvers do a good job with that. What's hard to do is if you're going to lay out the points for trajectory optimization and a priori say, I'm going to put a bunch of points right here because I need to have stiff, I need to have higher order accuracy at this certain point, and then low order accuracy. It's harder to do that a priori. A stiff differential equation is one where the characteristic timescales change a lot across variables or across time. So basically, you have some numbers that are coming out really big and some numbers that are coming out really small. So if you have, like, my mass is on order 1, and then my spring constant is on order 10,000 in order to avoid penetration, then the differential equations x dot 1 might have units 1 and order 1, and then x dot 3 might have order 10,000, and then any method that's based on a sort of gradient-based estimation of the integral will start being confused by that and have to slow down. So the question was, if you were to let your trajectory optimization move the knot points, does that help with it? I think it could help with that, but you would have to then put the something about accuracy into your cost to force them to move and try to be more accurate. And that is possible. It's a little gross in some sense, because now you might have a solution that is less good for the robot, but you're competing with an objective that's just trying to make your solver good. And in practice, people haven't done that as much. We've not done that as much. Yeah, I think you could, but I think there's better ways. But really, you also just need a lot of points to simulate these, because the time step that the numerical integrators end up taking is very small. And in trajectory optimization, as you get too many, that's really the reason. As you get too many points, it just gets boring to watch it try to solve. Okay, went out of order here. The other thing that happens is we've got the bigger dimensional state space, but I think that one we're not going to be able to get around. Okay, so there was a subtle thing that happened in our minimal coordinates. There was, one thing was that we made the dimension of the state space smaller, but the other thing is that we actually avoided the spring model stiffness by, when we derived the equations of motion, we put a pin joint here. And somehow we thought of that not as a soft constraint with high gain, but as a hard constraint, which we could solve away with our Lagrangian mechanics by just writing a pin joint there. I mean, it sounds fancy, but we can solve away with our mechanics, and that made a difference numerically. You can do that in the maximal coordinates too. And that's what we're going to do, okay? So you can think of this as a constraint, but a penalty constraint, and we can turn that into a strict constraint. And if we handle it well, then we can get some of the numerical benefits of, if you could tell your solver that this constraint is active right now, then the solver has the opportunity to think about a constrained solution along that. Your trajectory optimization has an opportunity to think about that. Your feedback control has an opportunity to think about that. If you can tell it this is the constraint, it'll be satisfied over the next time, dt, then that becomes a numerically better thing to do. So for instance, now the constraints are, for instance, if foot I is off the ground, then lambda I equals 0. If foot I on the ground, this looks pedantic, but you're going to see we're going to turn these into equations in a second. Then lambda I becomes exactly the forces required to avoid penetration. Okay, so the picture you could have in your head now of the rimless wheel is, I've got a rimless wheel in space. There was a movie about that, by the way, right? Was it? I forget, what was the name of the movie where the like, Interstellar, yeah. Where the guy was totally a rimless wheel, right? Yeah. Okay, so, but now you have potential constraints sitting here, and you still write the forces. Okay, and we've called them lambda now, lambda 1, etc. Okay, but those forces are constrained to be either 0 or constrained to enforce a new constraint, which is a pin joint here, let's say. Okay, that's going to be a better formulation. So let's see how we write that out. So let's call phi of I, which is only going to be a function of the configurations, is the position of contact I. And I'm going to simplify right now into the case where you have a robot interacting with just the world, the static world. Of course, this can be generalized to pairs of robots colliding, or robots colliding with themselves and other things. But it's just easier notationally easier to say. I just have to worry about one guy colliding with known geometry. We're going to do it in the ground coordinates, if you will. Again, just so I can make my notation easier. It's not strictly required, but so this is now, it's going to be a three-dimensional vector, but I'd like to say that sort of phi of z is this way, and you can do x and y into the ground, right? So wherever the potential contact is, I'd like to have phi of z being my separation distance in the normal. Okay? In that case, if this is the location of my contact point, I have the J, the contact Jacobian, is actually just partial phi, partial q. And if I have many of them, I'll put an I here. Okay. And that happens to work out with all the mechanics that it really does describe the wrench that the contact force places on the rigid body in the generalized coordinates. Okay? That is the relationship, which you can derive pretty easily, but I won't. Okay, so our constraints here, if foot off the ground, start looking like things we can easily write in terms of phi and lambda. So we'd like to enforce that phi I of q is always greater than or equal to 0. Right? You'd like to never penetrate. That lambda, sorry, this is at least in the z direction, is greater than 0. Okay. Lambda of z is always going to be greater than or equal to 0. We define it to be similarly, the ground will only push away. You never pull on the ground. Right? And you can start writing down things like friction if you want. So you could say, for instance, that the magnitude of the xy components of this is less than or equal to mu times the z component would be a model of Coulomb friction. Okay, but most importantly, what we want to do is have this a notion of no force at a distance constraint, saying lambda has to be 0 unless phi z, lambda z has to be 0 and phi z is 0, right? And that's going to be done with this complementarity constraints. Which are often written like this: bi z q perpendicular to z and we already have that they're greater than or equal to 0. And it's often implemented as, for instance, bi z of q times lambda z lambda. I guess I'm dropping my I too often. Sorry. Equals 0. So this combined with those says that at least one of these has to be 0 at all times. This is potentially sort of an ugly nonlinear constraint. And the name of the game today is going to be, how do you think about that constraint well? One of the good things is that this constraint is not unique to contact mechanics. It comes up in any sort of constrained optimization world. So like lots of really smart optimization people have been thinking about how do you solve this numerically for a long time. In fact, when you were solving SDPs and the like, the solvers were thinking about that, those types of constraints to follow a central path in a SDP solver. Okay. So is that formulation clear? I can write down equations of motion using my favorite manipulator equations. Now the state space is bigger. It's the floating base coordinates as if there was no constraints. But I'm going to write down here the set of constraints that on that system in a very compact way relatively, which says, I could have made a big table, said if this foot is in the ground, and this foot is in the ground, and this foot is in the ground. I didn't do that. I just wrote one set of constraints per contact point, which completely define my dynamics. If I can then simulate with this, or optimize with this, then I've got a good solution to my original equation. Okay. More importantly, by having this floating base coordinates, there is less mystery about how you connect things across different modes, right? So they're still you're always in the same coordinate system, okay? And as the system progresses, it's basically just which constraints are active at which time. That's all that's changing. The different contact modes are different active constraints. Now, an alarm bell should be going off in your head when I say that, because there is potentially a combinatorial number of different modes you start having to think about, right? So if I try to say something about for all modes, then if there are n possible contact configurations, and every one could be active or inactive in arbitrary, then you've got 2 to the n possible modes, right? And that does come back to haunt. Not always. There's some ways to get around it, but you can get hurt by that. It's actually even worse than that, because this is just in the sticking regime. If you have friction and sliding friction, then actually you have additional constraints for. So the standard way to model sliding friction is with maximal dissipation. So basically, if I am moving at all, then my contact force is the force that will take the most energy out of the system instantaneously, maximum dissipation, right? And you get another sort of complementarity constraint that models the sliding friction, whether you are sliding or not, in the same way. Either you're sliding and your force is on the edge of the friction cone, or you're inside the friction cone and you're not sliding. That's way uglier to write and requires slack variables, so I won't write it down, but it could be worse. So then if you have, at every possible configuration, many possible, you'd like to say Ford VN or something, but it's not, because the way people model friction, it can be a lot worse, okay? All right, so how do we use constraints like this in simulation, right? So what can you do to simulate this more accurately? Well, again, there are good tools from numerical simulation that can come into play. People know how to integrate constrained equations. In their most glorious form, they're differential algebraic equations. And you can go to DAE solvers. And the most accurate simulators for contact would be ones that could simulate, could do the event detection, and then use sort of a constrained equation solver in continuous time. That's probably the best, most generic way to write a solver like this. It's hard to write, and people don't tend to write that because they're not the most performant solvers. But it's a goal. It's a good goal to have that. There's another really subtle thing that I was thinking about saying about this notion of penetration. Okay, I said it was bad because of the stiffness of the differential equation. It's also the reason, if any of you have had the experience of using a state-of-the-art robotics solver and trying to pick up an object and it goes and shoots across the room, or we had the experience. I had sort of a set of videos for this, and I just thought that I don't need to go there. But there's videos of us walking in the DARPA challenge, the simulated version of the DARPA challenge, where our foot was kind of going like this. And in fact, one of the teams that won the virtual, was one of the teams that went on from the virtual challenge. The walking over the rough terrain was being simulated so badly that that they basically said, okay, the best strategy is actually to just fall down at the start line, vibrate your fingers, exploit the numerics of the simulator, and the robot sort of like translates itself across the ground. And they got to the finish line just as fast as the people who walked, and with a lot less stress, you know. So that's just the state of the art of solvers today, and that happens in both in a couple different ways. But it certainly happens in these models because it's a subtle thing. But once you have any penetration, then it gets very hard to maintain numerical accuracy, because if you have, for instance, you know, two bodies in contact. Okay, and it somehow comes in and penetrates. It's very possible, for instance, to enter in this space, and you're trying to build a spring model here, okay, and then maybe you just happen to cross a threshold, okay, and suddenly your spring model says, oh, I had a spring model here, for instance, right? And suddenly it's like you're ejected out of this space that you were never applying forces against. That is one of the symptoms that causes that. Okay, so as soon as you allow any numerical penetration, now the onus on penetration depth calculation, which is often shortcutted, goes higher, and even the best, you know, even the right penetration depth calculation can cause things to blow up. And it's sad. You know, it's frustrating and it's sad, comical at times, but. We found the way we could reset our robot to initial conditions in the virtual challenge was to you just cause a little penetration, the robot would go flying through the air and end in some random new configuration. That was sort of fun when you were playing with it, but sad at the same time. Okay, so there's another way that people do that. So the constrained differential equation solvers and DAEs are one approach. It's not the one that most people use. And the one that most people use is this time-stepping approach. Okay, and the idea is roughly that we're going to do a discrete time approximation of the continuous mechanics. Okay, we've done that. There's a couple of ways we can do that. For instance, you could do Euler integration. You could do higher order, more accurate integration. Okay, but in order to try to avoid these penetration issues, we're going to do with explicit non-penetration constraints enforced on every dt. Okay. So where solving a differential equation before was just multiplying a couple equations and you get the next outcome, now in these time-stepping methods, we're actually solving a small optimization on every time step in order to compute our next update. Okay? The optimization is written right there. It's the manipulator equations plus this. It's typically done with backward Euler integration to make everything work, but that's sort of in the noise for what we need to focus on right now. Okay? But it's roughly those constraints. Now, the problem is this is an ugly nonlinear constraint, and we're not sure, we have to think there's two nonlinear constraints floating around here. There's this one, and there's the Coulomb friction constraint. Okay? So as written above, what we would have is a nonlinear complementarity problem. Or NCP. If, however, we take that Coulomb friction constraint and make an approximation. So that's a second order cone constraint, it's called, right? You can imagine the picture of that is that if I plot lambda x, lambda y, lambda z, the picture of that is a cone, right? And that's, I hope that you can connect that to your intuition about friction. If you push harder, you get to have more frictional force, right? And the ground is allowed to do anything it needs to do inside that frictional force to try to keep you from moving. And then what I was saying about dissipation before is at some point, if I start sliding, then it'll have there's a frictional force that'll be at the boundary, which is trying to resist your motion. Okay, but that's it happens to be something that throws you into the nonlinear complementarity problem formulation. So people will often approximate this with polyhedral approximation. Okay, so I can just approximate that with some polyhedron, still a polyhedral cone. Okay, is that clear? Then I can write that Coulomb friction as linear constraints now. There's some really subtle things that happen inside. Like that picture doesn't look so bad, right? If you start looking carefully at the way the solvers use it, it'll make you cringe. Like for instance, the maximum dissipation. So first of all, a lot of people just use 4, right? Okay, just because that's super fast, right? But then maximal dissipation, the fact that your dot product of your sliding force and your velocity needs to be maximal means you're basically, when you're sliding, you're only getting forces from one of those 4 corners. You'd like to feel like you'd get it from anywhere on the surface, but in practice you only get it at one of those 4 corners by maximal dissipation. And I don't know, the more you dig in, it's like that's a sort of a gross approximation. Because what does that mean? That means that your dynamics are somehow dependent on the coordinates you happen to pick to represent your friction cone on the ground. Like you just change that and your robot will move a different direction. Yeah, it's gross stuff. But if you make that approximation, then you get a linear complementarity problem. And this is the stuff of where there's lots of good work in optimization. And there happens to be specialized algorithms that solve it really well, even though it seems like it should be hard. Somehow there's solvers that people can use to effectively solve those equations at interactive rates, at runtime rates. Yeah. Yeah, you can have as many faces as you want as your NCP, as your LCP. Sorry. Yep. But the cost goes up. So now if you go into the world, like if you look at computer games, how do computer games simulate computer physics, for instance? That's maybe the people that cut the most corners for performance, but that's their job, right? So yeah, they tend to use this, right? And they tend to only you get lots of these constraints. The number of possible constraints are combinatoric in the number of possible contact configurations. So what the solvers do in practice is they say, there's like 15 possible constraints that could be active. I'll choose 3. Because you want to have a fixed runtime, right? So it's like there's some number that's in the hard-coded. It says like, I'll take the 3 that look good, and I'll just enforce those, and I'll solve a fixed size LCP of a certain, size, and I'll solve that at a consistent runtime in order to get an interactive experience for people, and I think that's justified, but that's another reason why things blow up. But the bad thing is that our robot software does that too. So what can you do? Well, you can try to write a better solver. That's what we've been trying to do. But there's a bunch of corners that people cut in the LCP solvers. But when you watch, like if you use Bullet, for instance, and you watch Bullet, if you know it's an open source simulator, and you watch Bullet drop millions of crayons or dishes or blocks or whatever, and they're falling all over each other, it's shocking, but every one of those objects is written in maximal coordinates, and they're just solving constraint LCP in order to keep those, to run that simulation. If you zoom in and inspected every possible thing, you'd see penetration happening all over the place because they're only solving, they're cutting corners to solve it fast enough. But, visually it's amazing, right? In the virtual robotics challenge for Atlas, the top speed of our walking algorithm in simulation was limited by the LCP solver again, because even the rigid body equations in Gazebo, or at least when Gazebo is using ODE as its backend, are written in maximal coordinates. So joints are only held together by contact forces. And what happened is if you started your massive robot moving fast enough, then the joints started separating, okay, and then going apart. And at some point it got ridiculous, and our kinematics were wrong. We'd fall over. And we said, let's not spend time fixing that, because and actually the real robot turned out to be easier to control than the simulator at some point. Okay, so very cool. So for simulation, you can imagine given Q, right? So what does this LCP look like? It looks like a feasibility problem. To propagate my dynamics forward in time, okay? Okay. Given my current Qn and Qn dot, I'm going to find Qn plus 1, Q dot n plus 1, my contact forces at n, okay, and some slack variables for friction, but I'll continue to sweep those under the rug, okay. Find these subject to my manipulator equations being integrated with backward Euler. Okay, and then my complementarity constraints, Pi greater than or equal to 0, lambda I Q greater than or equal to 0. In practice, this gets a linear approximation of this, also to be a LCP. And then lambda I Q times Pi equals 0. And then any constraints you have for friction or I'll just write polyhedral friction. Okay, so it's a feasibility problem with extra decision variables, including your contact forces. It's ugly and nonlinear, but somehow LCP solvers are able to solve that really, really well. And in practice, you ask it to solve the smallest reasonable thing that makes your game look good. Okay, but this is somehow worlds apart from the hybrid world, because my hybrid event detection, if I was trying to simulate millions of bricks falling on top of each other with my hybrid event detection, the solver is going to stop for a zero crossing at always, basically. It's going to have to track this combinatorial number of possible active sets right? It's just not even thinkable. And this somehow being a compact enough representation where the number of constraints grows with the number of contacts, but not the combinatorics of the number of contacts, is something that people can do at real time. Okay? So we made some progress in the last few years saying, well, this has worked for simulation. Could it also work for trajectory optimization, for feedback control, for sum of the squares, right? And yeah, it can. Okay. So one more subtlety I want to make sure you capture here is where did the reset go, right? So there are two things that were happening in the hybrid model. One, or let's say even in the spring model. So the spring model, one of the reasons I have to have a stiff spring is not just that if I start my robot standing here, I don't want it to sink too far into the ground. That is, of course, one. But you also have to turn the stiffness and the damping up on the spring, because when the foot hits the ground, if you try to slow it down just with spring forces, those spring forces have to be relatively large to slow it down, because you're not doing explicit event modeling for that impulse. Okay? The hybrid models with the non-penetration constraint, they explicitly looked for that contact event. They performed a reset map, which was an instantaneous change in the velocity. So the picture, if you were to plot the forces over time, let me give myself more space. So for the hybrid case, if you were to plot over time, let's say B, I, Z with Q, let's say I went down here and made a contact and then came off the ground here. Okay, what are the contact forces going to look like? Well, we know they're going to be 0 here when this is off the ground and 0 over here. They're allowed to be non-zero here to resist the pull of gravity into the ground. But the subtlety is that in order to have it instantaneously stop, lose velocity here, right? There was an instantaneous change in velocity. That impact event looks like an impulsive force, a delta function here, right? So right? That's a delta function. And it sort of happens for real, right? So, okay, I run barefoot. It's weird, but I have been to a running clinic where they have an instrumented treadmill, and you can run on the treadmill and watch your ground reaction forces. Okay, the reason I run barefoot is this roughly. It's because if you look at a person running on a treadmill, their ground reaction forces, pretty much anybody running on a treadmill, there's a natural thing where you see this, and then you see this natural sort of, this is in the Z direction. You see this huge spike when your heel hits the ground or whatever, and then you see the sort of the weight-bearing ground reaction forces. In fact, I think the proportion is more dramatic even. Okay, and then there's this cool thing that happens for anybody. You take off your shoes and you keep running, and this goes down to like that. Okay, it's because it hurts if you land. If you smack, if you smack your foot down, it hurts, and so you learn not to do that. But then the idea is you save your knees when you're my age. But impacts are real, and they like you can see them in biomechanics, and they certainly see them in the simulator. Where did they go in the time stepping world? We didn't do any event detection in time stepping. But we also didn't get any penetration. What happened? Yeah. Yeah, I think that's right. Yeah. Right, so this thing gets spread, the solver, in order to achieve that stopping, will produce whatever force it needed to, which would be a finite time averaged approximation of that, in order to bring you to rest here. Right, so the forces in this, these have the interpretation as a time averaged contact force in the discrete time formulation. Okay, so that that's pretty elegant and pretty good. Like that feels very satisfying. I mean, impulses seem numerically bad or whatever, anyways. So to have that seems pretty reasonable. It's a little bit weirder to write down, to think about what the complementarity conditions are doing here at takeoff, because the way it's written, this says I'm allowed to have force if I have force sort of at the end of time, if I'm in contact at the end of time. So in order to take off, you actually have to be able to take off without any ground reaction force. That's the rules of the game as written. And you can do that. You just, you have to build up and have velocity, and you can leave the ground. But so it's not as elegant on that side, on the takeoff. Okay, so this worked for forward simulation. Does it also work for trajectory optimization? Okay, and the short answer is you can write down exactly those sets of equations as a nonlinear optimization problem, where you could just tell SNOPT that I have a constraint like this. Right? The LCP solvers can do that, but this was only a feasibility problem. The LCP solvers cannot take an objective function. If you wanted to simultaneously optimize a trajectory or have other constraints floating around that may not be nonlinear, you'll have to use SNOPT and ask how well does SNOPT handle constraints like that, which are ugly. If you think about the geometry of that constraint, it's an ugly sort of constraint for the solver. It's basically, right, if I plot lambda z, and I don't want to keep writing, because I'm about to write a q, okay? Right, so this says you're either here or you're here. Right, that's a hard thing to ask a solver to enforce. Right, it's not just discontinuous, but it's like, yeah, it's a mean question for the solver. So in practice, what we can do sometimes to help, for instance, is to approximate it with this and then push down. Right, so for instance, if we were to write diq times lambda I less than or equal to epsilon, and then bring this down, that's a way to help. Okay, but the idea of using this LCP as a trajectory optimization is something called contact implicit trajectory optimization. Now you can minimize over an entire trajectory, x and u. That's the way we've always done trajectory optimization. But we'll throw in extra decision variables for lambda. You can put your favorite cost function on it. And you can hand that to SNOPT. That's the algorithm. So unlike the trajectory optimization through contact we've done before, where you had to preordain a mode sequence, this one now, if the solver is able to chew on that ugly constraint, the solver is free to solve for the contact sequence. And that was the only way we were able to get trajectory optimization for fast runner, but it also works for taking objects up and things like this. When it works, it's still a local method, a local gradient optimization. It's a little bit better than you might think about local minima. So there's an important intuition. So let's say the bounce pass, okay? So imagine I'm just going to throw a ball from one side of the room to the other side, right? And there's an obvious ballistic trajectory I could take here, but let's say the optimal solution would be to bounce the ball there, okay? So let's say my initial guess of my trajectory optimization was here, and my optimal solution, given my function, was actually to bounce. So the question is, does the solver have any hope of realizing that there's another sort of a very different solution nearby that it could take when its initial guess is here? If your decision variables are only x and u, then you could use the same sort of time-stepping dynamics to update everything, but it would have no idea that there's this very different thing that happens over here. And this is a subtle point, but if you write it down like this, then you've told the solver explicitly about the existence of lambda. And it understands that if I needed to, let's say I couldn't quite get to my, I didn't have enough power, for instance, to get where I needed to go, it could realize, well, what I need to do is push up on this more with a positive lambda. What I need to do that is pull, in order to get lambda greater than 0, I have to pull it down to the ground. So in some sense, you're giving, by writing the formulation like this, you're giving the solver an opportunity to see this opportunity to use contact to solve the problem. So it's able to do more with, get around more local minima than this was actually the original motivation of the algorithm, was to try to tell the solver. How do you tell the solver about the possibility of contact? Okay. There's another, the other sort of dominant approach in this world of trying to plan through contact with trajectory optimization is a bunch of work by Emo Todorov. And he does shooting methods, and he uses this trick of allowing force at a distance to give the solver that same opportunity. So he'll allow force at a distance in intermediate solutions and then try to clamp it down using shooting methods. Yeah? When I'm done solving, I would like to have the strict complementarity. If my solver ran, got stuck in local minima or whatever, or was numerically bad for some reason, if the solver said I'm having trouble, which it does with different error codes, then you might try to do this, solve it once, get the initial solution from this, and then reduce epsilon till you ultimately solve this. Yeah, I don't know if Emo always does that though. So that's the complaint, because I think the shooting part has to get into the stiff differential equations for it to work. So there's a lot more to say about this. We can do the we could do the stabilization through contact too. Let me throw out a few extra ideas, right? So this LCP time-stepping method is a first-order integration. So it's only got first-order accuracy. The size of the time steps that you can take depend on your accuracy. It turns out that you can write it's hard to write here, but in the trajectory optimization case, you can do direct collocation. Right? You can't integrate with direct collocation, but if you're doing a trajectory optimization, you can do direct collocation. So you can do a third-order accurate integration on the LCP equations with a slight variation. So there's a co-location method, and that dramatically increased the accuracy of the simulations that came out. And the reason that we had to do that was because when you went to stabilize the solutions that were coming out of this, they were not stabilizable because of numerical integration accuracy errors. And so it wasn't until we got a higher order accuracy that we got enough higher enough quality solutions to stabilize. You can do LQR in the constrained coordinates. If you take a time-varying linearization, you also linearize the constraints. Then if you try to do LQR in the full coordinates, you will fail because the system is not controllable. But if you project down to the constrained coordinates, then you can write an LQR solution along the constrained coordinates, still with all your representations being in maximal coordinates, and your constraint being a time-varying linear constraint. Okay, and you can do sums of squares directly on these formulations, because this thing, love it or hate it, at least it's polynomial, and so it falls actually nicely into the sums of squares framework. And one of the really important observations, a lot of this work was done by Michael Poza when he was in our lab, and he's now at Penn. He's awesome. And one of his key observations was that if you write down the sums of squares conditions for Lyapunov stability using these types of equations, because of the way that the contact forces enter linearly, you don't have to solve the combinatorial number of possible contact sequences. You can think about the implications on V dot of each contact individually and still say something about their contribution in joint. Okay, so the big idea for this lecture was that, dealing with the constrained equations in floating base actually becomes a more effective way to talk about stabilization across contacts and planning through contacts. And I'll just, since I'm out of time, I'm going to just give you the highlight reel a little bit. You're going to hear more about how these work for humanoids in the next lecture. But so using the complementarity formulations of contact, this was at a time when we were working on the DARPA Challenge, but also when my kids were watching American Ninja Warrior. So we were trying to make Atlas do things like this, right? And these are pretty complicated contact scenarios, right? Like, watch the way this guy lands. That's style. And then, this is the salmon ladder, right? You guys know that. It's not like I was talking about MASH or something really old, right? This is like last year. Okay, these are all the different, I showed you the optimization before, but, these tools worked for a lot of different problems. If I had more time, I would go into the questions of how do you use trajectory optimization on the fly in order to use it as a feedback controller in a model predictive control. But we'll have to save that for a future lecture.